Hello, I'm Johanna Debrecht, and this is the first video in the Calculus 3 playlist. I hope you'll join me for many of these videos and learn a lot about Calculus 3. First thing I'm going to do is share my screen with you so that you can see the notes on the back more easily. However, you should still be able to see me up in the corner. So let me share my screen with you and we'll get started on vectors in 2 dimensions. So our course starts basically with a discussion of what vectors are. Now we're going to talk in this section about what vectors are in a 2-dimensional system, that is in a flat surface. So a flat plane like the screen that you see right here or the top of the table, 2-dimensionals, right? Like XY coordinate system. And then in the next video, we'll talk about vectors again, but we'll talk about vectors in the 3-dimensional system, which is, of course, the world that we live in. We've got an X, a Y, and a Z coordinate, right? We've got 3 dimensions, length, width, height, those kinds of things. So we're going to start today talking about vectors in the plane. Plane is the way we spell it in math, but we really are talking more about a plain, right? A flat area. So what we're going to start with is what vectors are. So we're going to start with an introduction. And I realize that many of you have probably already started calculus-based physics, so vectors are old hat for you, so this will just be a review. If you have not had calculus-based physics, this may be a new concept for you. So when we talk about vectors, we're talking about something that has both magnitude and direction. So magnitude would be like the size of it, the length of it. If we're talking about velocity, then it would be the 60 mile per hour part. That's the magnitude part. But a vector has both magnitude and direction. So when you're in your car, the speedometer is giving you your speed. Now, speed is not a vector. Speed is a scalar, right? It's just a constant number, 60 miles per hour. It doesn't indicate what direction you're going. That's not a vector. When you're in your car and you're going 60 miles per hour south, when you give the direction as well, that becomes a vector. And since we use north as positive, south as negative, east will be positive, west will be negative, the normal up is positive, down is negative, right's positive, left is negative in the math system, then you might call traveling 60 miles per hour south negative 60 miles per hour. Now, vectors, where they're positioned doesn't matter, all right? So if you're traveling 60 miles per hour north from Washington, D.C., it's the same as traveling 60 miles per hour north from Los Angeles. It is, in essence, an equivalent vector. They're the same, even though their locations, one's in Washington, D.C., and one is in, what did I say, Los Angeles? So you've got them on opposite sides of the country, but it doesn't matter if the vector has the same magnitude and the same direction. So again, when we're talking about vectors, it's got to have 2 components, the magnitude, which is like the length or the size of it, and the direction. Now, what we want to do is talk about how to write this stuff down. Now, when I'm typing and in my lecture notes, and if you want access to my lecture notes, just email me and I'll make sure you get them. When you're looking at it in a type something, we typically will use a bold-faced letter, all right? But you can't do that when you're handwriting. So when we're handwriting, we're going to use what's called a harpoon or an arrow over the particular letter. Now, we tend to use U, V, and W would be our most common, with U and V being the most common. And what do I mean by a harpoon? Well, a harpoon is like half an arrow, right? It's the mathematician way, the lazy way. All right, so it looks like this with just one barb on the end of it. Now you can also draw an arrow if you want. So this would be the same vector right here, vector U, but it just takes longer to draw, right? So mathematicians are notoriously lazy in writing things down. So we mostly use the harpoon. Now a vector can be represented by a directed line segment called a ray. So it has a ball at one end, which is the initial point, and an arrow at the opposite end, which is the terminal point. So the initial point is where it starts, and the arrow is at the terminal end, the direction that it's traveling in. Now, the magnitude of it is actually the length. So when you're talking about the length of this thing, whatever this is right here, if the length is 5, that's the magnitude. So that is the magnitude part of the vector. And then the direction is the direction that the arrow is pointing if you go from the initial point to the terminal point where the arrow is. All right. So how do we represent the magnitude when we want to write it down? The typical notation of what it should be is a double bar on either side of the vector. And this represents, of course, the magnitude. So in the case of driving 60 miles per hour north, then it would be the 60 miles per hour, right? It doesn't include the direction, it's just the magnitude. Now, again, we get kind of lazy, especially in upper level courses, and they're like, oh, they know what we're talking about. I'll just use absolute value. So you may also see this occasionally written in absolute value. It still means magnitude, all right? So it would be the 60 miles per hour or the 5, whatever the length of the particular vector is. Now, we do also have what's called the zero vector. And the zero vector is a really strange animal, all right? You might imagine it's a strange animal. It's 0 long. Well, how do you even draw something that's 0 long? I mean, that basically means that the initial point and the terminal point are superimposed on the same point, right? So you've got your beginning and your end in the same location because the length of it is 0. Now, we can think of it 2 different ways, and we'll typically think of it the second way. One way is to say that it has no direction because it has 0 length. So you can say it has no direction. This is not the way we typically think of it. What we typically think of is that if you have the 0 vector, it can point in any direction because it is 0 units long. And so we typically would call the 0 vector being parallel to any vector because it can point in literally any direction because it has a magnitude of 0. Now, in order to show the 0 vector, to make it different from the scalar 0, you have to put the harpoon or the arrow over the top of it. So this represents a vector that you see right here. This is a vector. And if you write it without it, this is a scalar. Now, a scalar in mathematics is just a constant, right? It's just a number. So in this case, it's the real number 0, right? So 0 without the harpoon is the scalar real number, and 0 with a harpoon is a vector. So it has both magnitude of 0, which is a scalar, and it has direction that could point in any direction at all. Now, that's not normal, right? I mean, normally a vector points in one particular direction. But because the 0 vector has no particular length, 0 length, then we say it could point in all directions, which is kind of weird, but that's sort of the way we think of it. Now, what about equivalent vectors? What happens for equivalent vectors? And what do we mean by equivalent vectors? Equivalent vectors have the same magnitude and the same direction, but they may not be located in the same place. That's why 60 miles per hour north is an equivalent vector from Washington, D.C., than the one going 60 miles per hour north from Los Angeles. They're in 2 totally different places, but their length is the same, 60 miles per hour, and the direction is the same, north. So it turns out that as long as the vectors slant in the same direction and have the same length, then they're the same vector, all right? They're equivalent vectors. So in this particular picture that you see right here, V1, 2, 3, 4, and 5 are all equivalent vectors. They have different positions, but they have exactly the same length and they have exactly the same direction, all right? Now, again, the initial point is where the ball end is, and the terminal point is where the arrow end is, and the direction goes from initial to terminal. All right, so we've talked about what equivalent vectors are. What makes them parallel? Well, obviously, if they have the same direction, even if they have different lengths, they're parallel. But what if one of them points in the opposite direction? So let's say, and again, you're going to have to work with me here because, you know, drawing straight lines is not my not my strength. So if you look at this one right here, this one looks like vector V, this vector v, but it points in exactly the opposite direction. You can tell it has the same slope, right? If we're thinking of it as a line, it's really a ray. But if you're thinking of it that way, it has the same slope. But this one's pointing in the opposite direction, 180 degrees opposite. So what we would say is that this one is basically v, but it's been multiplied by a negative, and that reverses the direction by 180 degrees. They're still parallel. They're still parallel even if they point in 180 different degrees. So either they point in the same direction or they're completely opposite, all right? Now, the next thing we want to look at here is another way of naming a particular vector. And this one is using endpoints, so like from P to Q. So when we're talking about going from P to Q, let's say that we have P here and we have Q here. So if we're talking about the vector PQ, and we put the harpoon above the top like so, like you see here, the P is occurring first, and it's under the end without the harpoon. That's the initial point. And then the Q is under the harpoon, so that's the terminal point. That means it has to start at P, and the arrow end has to be at Q, has to be. Now, this is not the same vector as QP. So let me do QP in blue. So here's vector QP. Now, what would vector QP do? Vector QP would start at Q and go to P, and the arrowhead would be in that direction. I kind of drew them side by side so you could still see them, but really they're laying on top of each other, right? Because P and Q are a point. I just made my point super big so you could see them. All right, so this is another way of naming a vector, where the one on the left is the initial point and the one at the end is the terminal point, all right? So the next thing we want to do is we just want to practice this real fast. And if you have access to my lecture notes, then you can practice this at home. We want to sketch the vector ST, where S is 0.3, -1, and T is -2, 3. So first thing to do, come to the origin, 3 to the right, which would be here, and down 1, which is here. Notice the scale is a little different here. Each grid is half a unit rather than 1 unit. So this is 3, -1. And then -2, 3 would be up here. Let me label my points. There's T and there's S. And I want ST. And again, it's always given in order with initial point first and then terminal point second. So ST has to start at S and go to T. And what I typically do is I typically keep either a credit card, an ID, an index card, a business card. All of these things make great rulers for drawing things. So I'm going to use my index card here, and I'm going to try to draw a straight line, which is always a challenge for me. So ST points in that direction right there. Now, if I had one in a different location that had the same slant and the same length, it would be equivalent, just in a different position. So keep that in mind, all right? Now let's move on to talking about the geometry and what happens when you multiply by a scalar. Now, we've already seen that multiplying by a -1 reverses the direction 180 degrees. So instead of pointing this way, it points completely in the opposite direction. All right, so a scalar, again, is just a real number. It's a constant in math and physics, and it has magnitude only, but no direction, right? So 5, that's a scalar. So if we take a vector and we multiply by a scalar, it can't affect the direction because the scalar doesn't have direction, but it does affect the vector's magnitude or the length of the vector. So when we're looking at that, what it's going to do, multiplying by the scalars, change the magnitude of the vector. It won't change direction, but it'll change the magnitude, unless we multiply by a negative, and that will reverse the direction, all right? Now, this is what we call scalar multiplication. So looking down here, basically, if we're going to use a scalar, then we'll typically use something like the letter K or something like that in italics. but not bold print. Bold print is for vectors only. So if we take our scalar k and we multiply by a vector v, then we'll get a vector that is whatever the absolute value of k is multiplied by the magnitude of v, with the same direction as v if k is positive and the opposite direction of v if v is negative. Now, what if the constant is 0, right? What if we take this vector and we multiply by the scalar 0? Then we would end up with the 0 vector, but not the 0 scalar. So if I take k times a vector, and I know that k is 0, this is basically 0, the scalar, times the vector. So this is a scalar. Oops, can't spell today. All right, scalar. This gives me the 0 vector. All right, so make sure that you understand that the 0 scalar and the 0 vector are not the same thing. The 0 vector can be thought of as pointing in all possible directions, any direction you want. So it's technically parallel to all vectors. And the 0 scalar is just the number 0, right? The real number that you see on the number line, right? Okay, so we've talked about parallel ones. We've talked about changing the length. And I just want to look at a picture right here. When you're looking at something like this, if they're parallel, then there has to be some scalar that you can multiply by one of the vectors to get the other one. All right, it has to be a multiple of the other one. If they point in the same direction, there's got to be, or if they're parallel, because if they point in opposite directions, you just multiply by a negative scalar. So there's got to be one that will make them equivalent. So in this particular picture, looking right here, going from the origin to 2, 4 is the black vector A. And then you can see in green coming out here to 1, 2 is half of A. And you can see that it points in the same direction as A. The green points in the same direction as the black, but it's literally half as long. All right, that's what we mean. All right, the length of the arrow, the length of the vector is the magnitude. And then if I want 3A, then it goes 3 times as long as A. So that's the vector in blue, again, starting back at origin. And this is what we call standard position. And we'll talk about that in just a minute. And then over here in red, you can see in quadrant 3 that we've got negative 2A. And because it's negative, it points 180 degrees in the opposite direction. And it's 2 times as long as the black vector that you see there. Right? And in this picture right here, again, we have examples of what it looks like if you have parallel vectors. This is V, this is 2V, half of V, and negative V is the same length as V, but points in 180 degree the opposite direction. Now we want to talk about how to add vectors together. There are 2 basic methods, but they're so close together. You know, it's really splitting hairs to say this is one method, this is another. They're so close. They're practically the same thing. Not quite, but close. Okay, so when we're talking about adding vectors, keep in mind that the only kind of vector you can add to a 2-dimensional vector is another 2-dimensional vector. You can't add a 3-dimensional vector to a 2-dimensional vector. They have to have the same number of components, all right? So in 2 dimensions, we have 2 components. In 3 dimensions, we have 3 components. And we might have something called R7 where there are 7 components. If I want to add something to an R7 vector, I've got to have another R7 vector. I've got to have something with 7 components. So we have to have the same number of components to add together. Provided that we do that, let's look at this picture right here. So when you're looking at this, you can see V here is pointing a little bit, you know, right of straight up, 90-degree angle. So a little bit into quadrant 2, if you will. And then we have W, which is sloping uphill off to the right. Now, this is what's called the triangle method of adding vectors. And I call this nose to tail. Nose to tail. And the nose is the initial point of a vector, and the tail is the terminal point of the vector where the arrow is. Okay, so this is the ball, and this one down here is the arrow. All right, so to do nose to tail is to do the triangle method. So take one of your vectors, and it doesn't matter which one, you can do it either way. Take one of your vectors, here we took V, and then you want to stick the nose to the tail of that vector. So you want to stick the nose, which is the initial point of W, to the tail of vector V, so nose to tail. So initial point of the second vector on the tail of the first vector. And then once you do that, you connect the two ends of the vectors, and that's going to give you a triangle, all right? So this red vector that you see here is actually V plus W, all right? So you get V plus W. Now, you may say, yeah, but I would have thought of putting V at the end of W. Okay, well, if you put V at the end of W, and I don't have a lot of room here, but let's stick it out here like this, then I would still connect like this, and note, oops, my bad. And erase, and scroll back down. So obnoxious. All right, shifted on me. All right, then I would still have this coming across here. So here's my vector V again, and this right here would be V plus W, right? Now you may go, but those aren't in the same place. No, they're not. But V plus W has only magnitude and direction. It doesn't have position. And these vectors here, the blue and the red, are the same length and they point in the same direction, so they're the same vector. That's it, all right? Now, vector subtraction, there are two methods of doing it. One of them tends to mess students up then when they do vector addition. So I recommend doing method 2. Method 2 is basically just add the opposite. So if I were going to add the opposite, it would mean to take a vector, and then instead of thinking of it as U minus V, think of it as U plus a negative V, all right? So what would a negative V do? Well, it would point in 180 degrees the opposite direction. So for example, if I was looking at something like this, and I had my negative W, my negative W, of course, is going to point in the other direction, right? So it would point like this, okay? So everybody see that? This is parallel to W, same length, but in the opposite direction. W is pointing pretty much to the right, a little bit down. And if I look at negative W, it's pointing to the right, just a little bit up, right? So when I look at those, I could then connect the third side to make my triangle right here. And I would get the same vector as over here, given that I can't draw, all right? And that gives you negative W right there. And then this side right here gives you V minus W, right? Now, the other method is to take the two vectors and put their initial points together, and then to connect the third side. Now, if I connect going up this way, I have V minus W. And if I connect going this way, then I have W minus V, all right? And again, that kind of messes students up a little bit, so I generally don't use that method. I just add the negative of the vector and then do the triangle method, and that works out pretty well. And that generally is preferable, all right? Now, there is another method, it's called the parallelogram method, and it's pretty much related to the triangle method. In fact, you can see it right here, all right? It's already there. Do you see that you have a parallelogram, all right? This vector and this vector are parallel to each other. These vectors are parallel to each other. And you've got the same thing going on here. So we've got a parallelogram. Now, when we're adding them, and we have this parallelogram that we see right here, remember, we usually do nose to tail. And so this is V, and this up here would be, again, W. So here's W right here, all right, translated with the nose to the tail of V. And then we know triangle method would connect the 2 points right here, starting at the initial point of V and going to the terminal point of W, and that's V plus W. And again, it has to go in that direction, from initial point of V to terminal point of W. But you can also draw vector W on both sides and draw vector V on both sides, and that gives you a parallelogram. And then the diagonal of the parallelogram becomes the addition of the two vectors. And in that case, then you're going to go from the initial point of both V and W across to the opposite corner, and that gives you V plus W, and that's the parallelogram method. Now, this is adding them geometrically. There is obviously a better way to add them, and we're going to be talking about that soon as well. And that is basically to use the components. But we haven't talked about that yet, so we'll get to that in just a little bit. Now, the next thing that we want to talk about is the triangle inequality. This comes up occasionally. And when it does come up, we kind of need to have that piece of information. So the triangle inequality is referring to the magnitude of vectors when you add them together. And it basically says that the length of V, the magnitude, plus the length or magnitude of W has to be greater than or equal to the length or magnitude of V plus W. And this should make sense to you, because if they were equal, then it wouldn't make a triangle. They would lay on top of each other. They'd have to be pointing in the same direction. If you were to superimpose V onto V plus W, it would come to about here, and then W would extend beyond the point of V plus W. So the magnitude of V plus the magnitude of W is usually longer than the magnitude of V plus W. The only time that they're equal is when V and W are parallel. That's the only time that they're going to be the same. All right, when they have the same direction, then you can get these two to be equal to each other. So the less than or equal to includes the degenerate triangle case, where what you really have is two vectors in the same direction. So this will be U. And let me choose a different color. This will be V. And then U plus V is just the length of the two together. And that's U plus V. Okay, that doesn't show up too well, but you get the idea. So this is a degenerate triangle, because it doesn't make a triangle, does it? No, it does not. So the typical case where you do have a triangle, the magnitude of V plus the magnitude of W is going to be longer than the magnitude of V plus W. And that's called the triangle inequality. Okay, let's take a look now at example 1. In example 1, we're going to use either the triangle method or the parallelogram method to add the vectors with initial point at the origin and terminal points at 2, -3, and 5, 1, respectively. So we want to add those together. So the first thing we want to do is put them out here. So we know our initial point on both is at the origin. One terminal point is at 2, -3, which would be here. So where's my straight edge? We'll draw this one coming down here. Okay, roughly. All right, and then we can draw our other one, which is going to be going from the origin out to 5, 1, which would be 5 up 1. So that would be this one right here. Let's see if I can get that. Oops, I went a little crooked. Okay, that goes out to there. All right. So we've got our two vectors here, and I want to add them together. Well, how do I do that? Okay. Now I said put nose to tail, but I didn't actually show you how to do that on a graph. So what you do on a graph is you look at one of the vectors, and it doesn't matter which one, either one. I'm going to say the blue one since it's shorter. And I look at the vector, and I actually am looking at the slope. So I know that I go down 3, right 2. So I'm going to go over here to the terminal point, right? And I'm going to put nose to tail. So I'm going to move this vector from being positioned at the origin to being positioned at 5, 1. And I'm going to do exactly what it says. I'm going to go down 3, and let me do this in a different color. So I'm going to go down to 3, right 2, 1, 2. All right. So here's my vector, right? And you can tell that this gray vector is the same length, same direction as the blue. And then I connect. And when I connect, I want to connect from the initial point of one of the two I connected nose to tail to the terminal end of the other one. So it's going to go from the black one at the origin to the terminal end of the gray one. And that would give me, if I can draw it straight, this one right here, right? So that is my vector for adding those two vectors together. And you may say, okay, I see the triangle method, but where's the parallelogram? Well, the parallelogram would not have drawn that vector first. What it would have done is taken this blue vector and drawn it at the tip of the black vector. And then it would have taken the black vector and drawn it at the tip of the blue vector. And so I would have drawn that one, which goes right 5, up 1. And let me put that one in black as well. And then I would have had, as you can see here, a parallelogram, and the diagonal from the initial point of both out here to the opposite corner, that diagonal becomes the sum of those two vectors. Let's take a look at example 2. In example 2, we're given vectors. We're not actually told where they are. They're on a grid, all right, but we don't know where the origin is, so we really don't know where they are. And we're asked to sketch u plus v, u minus v, and 2u, right? And I reproduced all of them down here so you could see them all at once. So let's do u plus v. So practice along with me at home. Take either u or v and put it nose to tail with the other vector. I'm going to move vector u that you see right here. And so I'm going to take vector u, and I'm going to move it here to the tip of v. Now, u goes up 1, right 1. So I'm going to go up 1, right 1, and I'm going to put that there. And then I'm going to draw u again. So there's u. And I've got nose to tail. I've got the initial point of u at the terminal end of v. And then I'm going to connect from the initial point of v to the terminal end of u. And that will give me u plus v, which goes pretty much straight up just like that, u plus v. Mine's a little off because I'm using an index card. All right, let's see if I can get it a little closer. If I can get it more exactly on the line. Nope, same place. Let's try it again. There we go. There's u plus v. All right. Now let's take a look at u minus v. To do u minus v, I have to take u and put negative v nose to tail at the end of u. Negative v, v goes up to left 1. So negative v is going to go down to right 1. That would put it 180 degrees. So total opposite. Instead of up 2, I go down 2. Instead of left 1, I go right 1. So I'm going to go down 2, right 1, but from the terminal end of u. So down 2, right 1 puts me right there. And then I'm going to connect. And this right here is negative v. It's not v, it's negative v. And then the triangle method says, connect the initial point of view with the terminal end of the vector you're adding to it, which is minus v. And that's going to give us this vector right here, right? And it goes in this direction, right? So that you can see it, right? Now, what about 2u? 2u is really pretty easy. U goes up one, right one. So go up one, right one again, and that doubles the length of it. So 2u is going to start in the same place as u, and it's going to go all the way out twice as long. So it's going to be there. So its initial point is at the same place as u, but it just follows the slope pattern twice instead of once. All right, vector notation. So we're going to get to what we call the vector notation so that we can find and use the more simple method of adding vectors together, which is to add components. It's as easy as it can be. So when we're looking at this, remember that equivalent vectors are the same when they have the same magnitude and same direction. And you compare the slopes of the line segments in order to tell whether they have the same direction. And then the opposite direction just means you have a negative scalar there. So what is a standard position vector? Well, we have all these vectors that we've got up here that we've drawn in different places. Now, these vectors right here are in standard position. And they're in standard position because their initial points are at the origin. Now, they don't have to be there, of course. We also saw some that were located in different places. I don't see any offhand, but I will make up one. So I could say that this point right here, that's the origin. So here's the x-axis and here's the y-axis, all right? So we've got the two x-axis. I guess it's not really a vector. All right, so we've got the origin down here in the lower left. Well, u is still up one, right one, but it's not in standard position. To put it in standard position, I just shift that up one, right one down here with the initial point at the origin. And so this right here, this is u in standard position. It's still u, even if it's not at the origin for its initial point, but it's u in standard position when it is. Now, why do we like that so much? Well, because we know the origin's coordinates are 0, 0, and they never change, right? It's always 0, 0. So then we can refer to a vector in standard position by referring to the ordered pair at the terminal point. So in the case of u, we could call this 1, 1, right? Because it terminates at the ordered pair 1, 1. But we want to make sure that we can tell the difference between an ordered pair and a vector. So what you will typically see is angled brackets, and you'll see it written as 1, 1. And this is the vector that starts at the origin and ends at 1, 1. And when you write it like this, it's an ordered pair. It's a point, all right? So it's a point. And this would be the terminal point of that vector, right? Now, I will tell you that in some classes, especially when you get higher up in mathematics, they start getting lazy about the angles and they start using, yes, you've got it round parentheses, which can be a real nightmare, right? If these weren't the same number, it could also be an interval. So is it an interval, a vector, or a point? Well, you have to know the context. That's why I prefer the angle brackets, and that's what I'll use all the time in this class to represent a vector in standard position. All right. So this is what we call a vector in standard position, or just position vector for short. That means that the initial point's at the origin and the terminal point is at AB, and we use angle brackets to indicate it. And you can see down here, this is called component form of the vector. And you can see that it has the components, the X and Y components refer to the ordered pair coordinates of the terminal point. All right, so those are the components of the vector V. And again, this is in standard position, so you know the initial point is at the origin. And since vectors are the same, no matter where they're located, we might as well locate them at the easiest place, which is with their initial points here at the origin, right? And that's an easier way to go about that. Okay. In this particular picture right here, all but the translated vector negative b are in standard position. Now the translated one is actually this one right here. So this vector over here, this is not in standard position. All right? And that's because its initial point is right here. All right? So this one is not in standard position, but the others are in standard position. So the ones that are in standard position include the b vector, the a vector, and the negative b vector when it's represented down here in the gray. All right, also the red vector, which is a plus a negative b. This guy is also going to be in standard position. And this one down here is not, right? And that's because the initial point, again, is over here, which is not the origin. So it's a vector, it's just not in standard position. So let's take a look at this example. Which of these vectors are the same vector? Again, position doesn't matter. It's just length and direction that matters. So A is up to right 1. B is also up to right 1. So A and B are definitely equivalent to each other. D is obviously not parallel, so it's not. F goes up 3, not 2. So it's not going to be equivalent to A, B, or D. C goes up only 1 and right 3, so it's not equivalent to any of the ones up here. But E also goes up to right 1. So A, B, and E are all equivalent to each other. All right, they're essentially the same vector, just located in different places. So we would say A, B, and E, if I can quit erasing while I'm writing. All right, so now we're going to talk about the rule for component form and how to add things together when you're in component form. It's exactly what you would want the rule to be. It makes it as easy as you possibly can. So when we're writing something in component form, what we do is we take the terminal point and we subtract the coordinates of the initial point from it. So it's going to be terminal minus initial. So it's the arrow end coordinates minus the ball end coordinates. So this would make it x2 minus x1. Now, when you're looking at something in standard position, this is why we like standard position so much, because the coordinates of the initial point are 0, 0, and subtracting 0 from something doesn't change it. So that's why the component form is just this right here. So let's go ahead and give the component form for the vector going from C to D. So from C to D, and we're going to draw it like that. Again, what I have right here is I need to come up with the ordered pairs. So C looks like it's at 2, 2. So this is the ordered pair 2, 2. And D looks like it is at 7, 4. And so in order to find CD, I'm going to take the 7 and subtract the 2 and the 4 and subtract the y coordinate 2. And this will give me the vector 5, 2. All right. So it's the vector 5, 2. 5, 2 refers to it in standard position. So if I were to put 5, 2 on here, you would see that it is, in fact, the vector AB, 5, 2, and it is the same length and the same direction as vector CD, right? So that's basically how you find a vector from an initial point and a terminal point. Take the terminal point coordinates and subtract the initial point coordinates. All right, so let's practice with example 4. So in example 4, Vector W has initial point -4, -5, and terminal point -1, 2. Express W in component form. You really don't even need the graph, but we can certainly use the graph to check our work. So initial point is -4, -5. So we're going to take terminal minus initial. So this is going to be vector W. We use angle brackets. So -1 from the terminal, minus a -4 from the initial, comma, 2 from the terminal, minus a -5 from the initial. Double negatives make it plus, and you end up with 3, 7, right? So let's go ahead and put this up here and see that they are in fact the same length and parallel to each other. So initial point -4, -5 would be down here, and terminal point -1, 2 would be here. So this is what our vector looks like. Now this is the vector not in standard position. So it starts here and goes to here. And in standard position, we would go to 3, 7, 6, 7, which would be here. And it starts at the origin. Which would be this vector right there. And you can tell they're parallel and they're the same length. So they are equivalent vectors, right? And again, you don't need the graph in order to do it in component form. You just need the coordinate pairs for the initial point and the terminal point, right? Now let's talk about finding magnitude and direction. Now we talked about magnitude being represented with a double bar on either side of the vector, or maybe just the absolute values around the vector. And basically, when we get into a vector, what we're really using is the Pythagorean theorem. I mean, if I've got a vector x and I've got a vector y, and I'm trying to figure out the vector here, well, if I'm looking at this right here as my vector, this hypotenuse, well, I know that I could find the length of this by taking the x and squaring it, and the y and squaring it, adding them together and taking the square root. That's just the Pythagorean theorem or distance formula, however you want to think of it. So basically, the length of the vector is given by the x component squared plus the y component squared, and then you take the square root. It's just the Pythagorean theorem, right? So that will give you the length or the magnitude of the vector, right? Now, what is the length of the 0 vector? The length of the 0 vector is 0, the scalar. So you can see up here that we've written it this way. So if I want to represent the magnitude of the 0 vector, I have to have the harpoon over the 0 there. And this gives me 0, the scalar, right? And this is the vector that you see right there. All right. Now that we've talked about that, let's talk about the direction. Now, when we're talking about the direction of a vector, we typically, although not always, depending on the problem that you're solving, but typically we're talking about the angle between the vector and the positive x-axis. That's normal. However, a problem may say that the angle is between the positive y-axis and the vector. So you have to be careful and make sure that you're measuring theta from the right place. But if it doesn't say, then we typically measure from the positive x-axis. And again, we rotate counterclockwise, the typical trig fashion. And the direction of the vector can be described by this angle theta that the vector makes with the positive x-axis. Now, you know how you can find theta, of course. You need arctangent, right? So arctangent, you're going to, tangent, of course, would be the opposite over the adjacent. And arctangent would give you the angle theta. So when we're looking at this one right here, we have these components right here. So this is y, which is equal to 2. And this is x, which is equal to 4. And so we know that the tangent of theta is going to equal y over x, opposite over adjacent. And this is going to basically give us 2 over 4, or 1/2. And then in order to find theta, we take the arc tangent or inverse tangent function, all right? And so we look for the arc tangent of 1/2. So we're looking for the angle whose tangent turns out to be 1/2, all right? And that would be the angle theta right there. That's not one of the ones we memorized, so I don't know what that one is, right? But that's what it would be, all right? We can do arc tangent of 1/2, and you can get it in radians, or if you want, you can do it in degrees, although I stick to radians for the most part. Okay, let's take a look now at example 5. In example 5, we have a vector A in 7, 1 in standard position. B is the vector starting at 3, 2 and terminating at -1, -1, obviously not in standard position. Draw both vectors, then put V in standard position, find their magnitudes, find the direction of vector A in radians. Okay, all right, so I got to do all of that. All right, so let's just start with drawing the vectors. 7, 1 is the first vector. That's A. So I've got this down here. So 7, 1 would be here. And I'm just going to eyeball it this time. So this is vector A that we see right here. And vector B goes from 3, 2 to -1, -1. So 3, 2 to -1, -1, which is right here. So like that, all right? So this is B. And then they asked us to draw B in standard position. Now, what does B do? It drops down 1, 2, 3, and moves to the left 1, 2, 3, 4. So down 3, left 4. I think that's what we said. So let's do that one in a different color. Down 3, 1, 2, 3, left 4. So it's here. So it's this vector right there. Right? So that's what B looks like. And you can tell it's parallel to B, right? It's same direction. And so we've got that one down there. Now, the next thing that it asked us to find, and this of course is also B, right? It's just in standard position. The next thing it asked us to find was the magnitude of each one. Now, in component form, which is the angle bracket 7, 1, it's super easy. All you need to do right here to find the magnitude of A is just take the square root of 7 squared plus 1 squared, which is 49 plus 1, which is 50. So we get the square root of 50, which gives me 25 times 2, or 5 square root of 2. That's the magnitude. That's the length of that particular arrow. So when I come down here, and I look at this one right here, that's the length of it. Now, to find the magnitude in the other vector, if I worked in this initial, I would have to figure out what the x and the y are, which is basically the how far down and how far left we went. But I can do it from the standard position more easily by looking down here. This terminal point is at -4, -3. I think that's right. I said I went down 1, 2, 3, left 1, 2, 3, 4. Yeah, -4, -3. So the magnitude of vector B is going to be the square root of -4 squared plus -3 squared. So this gives me the square root of 16 plus 9, which is 25. And so the length of that vector is exactly 5. Okay. Now, I think the last thing we were asked to do was find the direction of vector A in radians. And it doesn't specify where the direction's being measured from, so we'll assume from the positive x-axis. So we want to look at this right here. We want to measure this angle theta. And this angle theta is basically this angle right here, right? So what do we have? Well, if you think about it, we have this really long, narrow angle that we've got right here. And we know that this length right here is 5 square root of 2. We know it goes up 1 and it went right 5. All right, so we know those pieces right there. From the Pythagorean theorem, we used those, or wait, no, not 5, 7. My bad. I got 5 on the brain. 7. 7 to the right, up 1. And we use those to find the magnitude. Now, if I want to find theta, I need the arctangent of y over x, right? So theta is going to be equal to the arctangent of y over x. And this is going to give me the arctangent of 1 over 7. Now, you were asked to find it in radians, so we do need the actual value for this. And if you put this into your calculator, you're going to get approximately 0.1419 radians, which is a pretty small angle, as you can see right there, right? Remember that if you go 90 degrees, basically is 1.57 radians. And so you know that 0.1419 is really small. All right, I believe that was all we were to do in this particular problem. So the next thing we want to do is talk about the algebraic vector addition and scalar multiplication. So when we're talking about algebraic vector addition and scalar multiplication, we showed how to do it from a geometric standpoint on the graph. But we can also do it without the graph and just using the components of the vector in standard position. And the method is really easy. You're going to love this. So if I want to add vector v and vector w together, and in component form, they are x1, y1, and x2, y2, with the ordered pair x1, y1 being the terminal point of v, and the ordered pair x2, y2 being the terminal point of w. Then to add the vectors together, I add the components together. I know, you're thinking it can't be that easy. Yes, it's that easy. So you just add the components together. So that does it. I mean, that's about as easy as you can get. Add x's to x's and add y's to y's. When you do scalar multiplication, it's very, very similar. If you have a vector v given by x1, y1, and you want to multiply v by some scalar value, 1, 2, -4, then you just multiply each component by that scalar constant, and that gives you the new vector, right, in standard position. All right, so we're going to start in example 6 with the same vector 7, 1, and b is the vector -4, -3, which is the one from the previous example. And we want to find 3a minus 4b. All right, so if we're looking for 3a minus 4b, then we might want to find 3a first. So 3a is multiplying by a scalar. So we have 3 times vector a, which is 7, 1. And that basically gives me 21, 3, because I multiply 3 by 7 and 3 by 1. It just multiplies each component by the scalar. And then I might want to find 4b. And of course, addition and subtraction are defined the way you think it would be. So this is 4 times -4, -3. And this would give me -16, -12. And then to find 3a minus 4b, I take those two new vectors, 21, 3, and -16, -12, and I subtract the second from the first. Now you'll notice the second, now we've got the subtraction, which is like plus a negative. So could I distribute the negative and just add? Yes, you can. It does exactly what you think it would do. All the rules that we have from arithmetic still apply. And so you could write this one as 21, 3 plus 16, 12. And you're going to end up with, I believe, 37, 15. Right? So hopefully that makes sense to you and you can kind of see how that works. Let's say that we want to find 3u, given that u is 5, 4, then 3u is just going to be 3 times 5, 4, which becomes the vector in standard position 15, 12, right? So it's really as simple as you might hope that it would be. It's pretty straightforward, not too difficult. Okay. Now we want to talk about some properties of vector operations, so you know what you're allowed to do from arithmetic and what you're not allowed to do from arithmetic. So when we're looking at these, we do have for vectors many of the properties that we have with the real numbers. They are commutative. U plus V is V plus U, and that's because when you add their components together, their components are scalars, and scalars are commutative, so you can always commute them. And then associative property, U plus V, then add W, is the same as U plus add V plus W first. So the associative property also applies. And the reason is the way we define vector addition, we're adding components, which are just real numbers, scalars, and those have the associative property, so it carries over. We have what's called the additive identity property. If you add the zero vector, this is bold, the zero vector to any vector, you get the vector back again, which is what you think would happen. And then if you take a vector and you add its opposite, you get the zero vector. Now, this was at one point a typo in the book. They did not have this bolded, and it should be bolded. It's a vector, not the scalar. If you take two constants and multiply by a vector, you can either do them one at a time, or you can multiply the scalars together and then multiply by the vector. So you have associativity of scalar multiplication, right? Which is you would probably expect to have. And then we've got R plus S times U. So if you want to add two constants together and then multiply by the vector, you could distribute the constants over the vector and then add together. So the distributive property of scalars over a single vector applies. And you also have the distributive property of a scalar over two vectors, which also applies. So you get R times U plus R times V. That's what you think it would do. We also have the multiplicative identity, which is 1, the scalar 1. 1 times any vector gives you back that vector. And then we have the zero property. And again, this was a typo in the book. They missed some of the boldface. The scalar 0 times a vector is the vector 0. So this should be a scalar. And this should be the 0 vector. And you do want to make sure you know when 0 is the scalar and when 0 is the vector. You need to know which one's which, right? Now, we've already talked about the components of a vector forming basically the legs of a right triangle with the vector as the hypotenuse, right? So dividing it into its components because it starts here and it terminates here. And if its initial point is at the origin, then we just use the ordered pair from the terminal point for the components of the vector in standard position. But this also means that because of right triangle trigonometry, that given the angle and the magnitude, we can actually use the cosine and sine of the angle to find the components if the vector is not given. So if we know that the angle is theta, and we know that the vector is 5 units long, say this is 30 degrees, we know this is 5 units long, we'll be able to come up with the terminal point in standard position using cosine and sine, and you get this relationship right here. So in other words, the x component down here is just the magnitude of the vector times the cosine of theta. Why does that work? Well, that's because cosine of theta is equal to x over r, where r is the hypotenuse, basically. And in our case, that is the magnitude of v. So we basically have x over the magnitude of v. And then to find x, we take the magnitude and multiply it by both sides. My harpoon. And I get the relationship that you see down there at the bottom. So it's just coming from the definition of cosine as adjacent over hypotenuse. And then the hypotenuse, the magnitude of it, the length of it, is the length of the vector. So you multiply that on both sides. And you get the same thing for sine, right? Sine is opposite over hypotenuse. And the length of the hypotenuse is the magnitude of vector v. So if you multiply that by the sine, you just get the numerator part, which is the y. Let's take a look at some of the examples that we have down here for component form. So we're going to go ahead and just run through these. It won't take us very long. They're going to be pretty straightforward and not terribly long. So when we're looking at example 8, we want to write the vector shown in standard position component form and give the horizontal and vertical components of it. So looking at this, it's in standard position, which must mean that this point right here, the initial point, is the origin. And then, well, then what would that make these coordinates? So this one down here must be the origin. And this one up here is right 2, 3, 4, up 1. So 4, 1. So this vector, we'll call it U, has to be 4, 1 in angle brackets. And that's the vector in standard position, all right, the component form of it. And now we want to know what are the horizontal and vertical components of it. Well, you have them, basically. Your horizontal and vertical components are given up here, and you could figure them out by looking at this particular thing. But I want to demonstrate, if I will, the process of doing this. So I'm going to go through the process in case that you didn't have all of this. And again, that's because we pretty much already know what the components are, but they're 4 and 1. But if we wanted to do this, we could also use the magnitude of V times the cosine of the angle. The angle would be the arctangent of 1 over 4. So the angle theta here would be the arctangent of 1 over 4. That again is y over x. We know the components are 4, 1, so y is 1, x is 4, so that would give us that. And then again, you could find the x component, which should be 4, by taking the cosine of that angle and multiplying by the magnitude of the vector. Now to find the magnitude of the vector, again, remember that you're going to take the square root of each component squared. It's basically the Pythagorean theorem in 2 dimensions. And so when we add these two, I wrote 16 squared. I'm thinking ahead. So this is 4 squared, which is 16. So 16 plus 1 gives us the square root of 17. All right. Let's now take a look at example 9. In example 9, we're asked to find the standard position component form of a vector V, has magnitude 10, so it's 10 units long, and it makes an angle of 120 degrees with the positive x-axis. All right, so I'm thinking about a vector, so I'm going to kind of draw a scale here. So I have a vector, 120 degrees would be 30 degrees past the positive y-axis. So this right here, it's in quadrant 2, so this is 120 degrees, which I think in terms of radians, this is 2 pi over 3. All right, so we have 2 pi over 3 radians, and I want to know what is the standard position component form of it. I know that the magnitude here of my vector V is 10. So this is 10 units long. What I need, of course, are the units right there at the terminal point. But I'm going to have to use the angle, the position, and the length of it in order to figure that out, right? So what I've got then for the x component is going to be the magnitude of V times the cosine of theta, which is going to give me 10 times the cosine of 2 pi over 3. And of course, it's in quadrant 2, so cosine's negative. And it's a tall, skinny triangle, so it's a short x and a long y. So the short x is a half, and the long y will be root 3 over 2. So because it's in quadrant 2, it's a negative x. So this becomes 10 times a negative 1/2, which gives me a negative 5. All right, so I have a negative 5 for the component. And then the y is going to be given by the magnitude of the vector, which is 10, times the sine of the angle, theta. So this is going to give me 10 times the sine of 2 pi over 3. And the sine of 2 pi over 3, I said, was square root of 3 over 2. And of course, y is positive in quadrant 2. And so this gives us 5 square roots of 3. Right? So that means that my vector v in component form is -5, 5 square roots of 3. And that actually means that that's what the ordered pair is here at the terminal point, all right, of the vector. Okay, so hopefully this makes sense to you, what we're doing right here, figuring out where things are. We have just a little bit more to cover. A lot of this is definitional, again, so a lot of definitions in Calculus 3. Lots of things you have, new terminology you have to learn. Most of it is not difficult until towards the end of the course, the terminology. I'm not going to say the calculus isn't difficult, but the terminology doesn't get difficult till towards the end of the course. And then the last 1/3 of the course, there are some terms and concepts that are more difficult than what you've encountered before. So what's a unit vector? Well, unit in mathematics means 1. So a unit vector is a 1 vector, which basically means it has magnitude of 1. Now, it could point in any direction. We just call it a unit vector if the length of it is 1. And making a vector that's not length 1 into a vector of length 1 is called normalizing it. So this is called normalization. Now, if you take any non-zero vector, now you can't do this to the 0 vector because its magnitude is 0, and there's nothing you can do that's going to turn that into a 1. But if you take a non-zero vector, we can just use scalar multiplication to find a unit vector that points in the same direction but has length 1. And all you do is you take the vector and you divide by its magnitude, right? The non-zero magnitude. So for example, if I were looking at this vector right here, I already know, or do I know? I do know. I know that the magnitude of it is 10. And so a unit vector in the direction of v would be given by -5 divided by 10, 5 square roots of 3 divided by 10, that's a 5. And this would give me the vector -1/2, comma, square root of 3 over 2. And if you don't believe me, square the -1/2 to get 1/4. Square the square root of 3 over 2 to get 3/4. 1/4 plus 3/4 is 4/4, which is 1, and the square root of 1 is 1. So this vector is of length 1. So you just took the vector and divided by the magnitude of it. And that makes the vector point in the same direction, but only have length of 1. Okay. So let's take a look at example 10. We want to find a unit vector in the same direction as v, then we want to find a unit vector in the opposite direction as v. So to find a unit vector in the direction of v, so we'll call this u in direction of v. This would give me, so let's call this u1. This would be 9 divided by the magnitude of v, comma, 2 divided by the magnitude of v. So I need the magnitude of v. So let's come over here and find it. Magnitude of a vector, remember, is basically the distance formula, finding the hypotenuse of the right triangle. So you square the x component, square the y component, add them together, and take the square root. So this is 81 plus 4, which is the square root of 85. So coming up here, 85, of course, does not have any perfect square factors. And this will give me 9 over the square root of 85. And this will give me 2 over the square root of 85. And this is a unit vector that points in the same direction. If you don't believe me, square these two, add them together, and then take the square root. And you're going to find out it gives you 1. Right? Now, how do I take a unit vector in the opposite direction? Well, once I have a unit vector in the same direction, all I have to do to get one in the opposite direction is multiply by a -1. The 1 won't change the length, but the negative will change the direction to the opposite. So we'll call this u2 in opposite direction of v. And this is going to be negative 9 over the square root of 85, comma, negative 2 over the square root of 85. Whatever the components are, just take the opposite of each one. In this case, they were both positive, so they become both negative. Okay. Let's take a look now at example 11, which says, okay, starting with this vector that's 9, 2, which is definitely not a unit vector, find a vector with magnitude 5 in the same direction as v, then find a vector with magnitude 5 in the opposite direction as v. Okay, well, this is the same vector we just did. How do I take this vector, which is not 5 units long, and it's not 1 unit long, and how do I make it point the same way, but be 5 units long? Well, it's gonna sound kind of easy, but what you do is you first convert it to a unit vector, which we've already done right here. And then we take the unit vectors and we multiply them by 5, and that makes them 5 long, right? So it's really that simple. So we take the vector, we make it a unit vector by dividing by its magnitude, and then to get a particular length, we multiply by that scalar. So let's go ahead and come down here and we'll do W1, which is same direction with a magnitude of 5. And the magnitude of W1 equals 5 is going to be 9 over the square root of 85, 2 over the square root of 85. So 9 times 5 is 45 over the square root of 85. And 2 times 5 is 10 over the square root of 85. Okay? And that gives you the same direction, but this time with a length of 5. And if you don't believe me, square these two, add them together, then take the square root. You're going to get 5, right? And what about W2, which is the opposite direction, but also of magnitude 5? Well, I could just take the one that's in the same direction with magnitude 5 and just point it the other direction by multiplying through by a negative. And so this one is going to be negative 45 over the square root of 85 and negative 10 over the square root of 85. Right? And that will make a vector exactly 5 units long that points in the opposite direction to the original vector v at terminating at the ordered pair 9, 2. Right? Now the next part, pretty much the last thing that we want to talk about are the standard unit vectors, also called the standard basis vectors. I've done a lot of linear algebra and we tend to call them the standard basis vectors there. So I may slip up and call them the standard basis vectors. They're the standard unit vectors. Unit vectors meaning 1 unit long, and they point in the direction of the x-axis or the y-axis. In 3 dimensions, they point in the direction of the x-axis, the y-axis, and the z-axis. And you can see them right here in their component form for both 2 dimensions and 3 dimensions. And notice that all the components are 0 except for 1. So 1, 0 obviously is terminating at the ordered pair 1, 0. So it's laying right here along the x-axis. So I is basically the unit vector in the positive x direction. Now, in physics, they tend to call this I hat. So we will do the same thing. And that's what you see right here. And it's pronounced I hat. But what we tend to do is do this. We don't actually make the dot for the I because that just gets too confusing. We draw the I with a little caret symbol on the top of it. And we call this I hat. It's actually a vector, right? So I hat is a vector of length 1 that terminates at 1, 0. J is the one that terminates at 0, 1, and we would call this J hat, all right, which of course is the vector J terminating at 0, 1, right? So you can see the vectors here on 2 different things, one on a grid, one not. Now you can express any vector in terms of I of j in what we call a linear combination. So for example, let's say you take vector v, which is x comma y. Then you know that you could split this up into two vectors because of component addition and write it as x0 plus 0y, right? So the x component by itself was 0 for the y component, and the y component by itself with 0 for the x component. And then you could factor the x out so that it became a scalar. And well, it was a scalar to start with. And then you would be multiplying by 1, 0, which is I hat. And then you could do the same for y. You'd be multiplying by 0, 1, which is j hat. Okay? So we would write this as x I hat plus y j hat. Right? And that's what you would typically see. And I'll refer to them as I hat and j hat because that's more common in physics. And I want to make sure I use pretty much the same notation when I can. It doesn't affect the magnitude, obviously. It's just another way of writing it. So let's say that we have a vector u with initial point -1, 6 and terminal point 7, -5. We want to write it in standard position in terms of I and j. Well, first off, it's not in standard position because the initial point is not the origin 0, 0. So the first thing I need to do is find the vector in standard position by subtracting the initial point coordinates from the terminal point coordinates. So vector u is going to be given by 7 minus a -1, comma, -5 minus 6, which would give me 8, comma, -11. That's in standard position, right? So it has the same length and the same direction as the vector starting at -1, 6 and terminating at 7, -5, but 8, -11 starts at 0, 0 and terminates at 8, -11. Now I want to write this in terms of the standard basis vectors. Well, there I go. The standard position unit vectors, which are I hat and j hat. And so, well, basically you just take 8 and stick it next to I plus -11 and stick it next to j hat. And of course, you don't have to write plus and -11. If you want to, you can write 8 I hat minus 11 j hat, right? And then you've written it in terms of the standard basis vectors or the standard unit vectors. And notice that this is not using the angle bracket form, right? This is the standard position vector forms. So I will ask on exams, typically I'll ask students to take a vector with some initial point and terminal point and write it in standard position, and then also write it in standard basis vector forms in the unit vector I and j forms, right? Let's take a look at number 13. We have a vector in standard position of 16, -11, and B is a unit vector that forms an angle of 225 degrees with the positive x-axis. And we want to express A and B in terms of the standard unit vectors, I hat and j hat. Okay, well, A is easy to do, right? A is pretty straightforward. There's not much to A. 16, comma, -11 in angle brackets is the same as 16 I hat minus 11 j hat, all right? That's it, we're done, all right? Now, what about B? Well, it's a unit vector, and it forms an angle of 225 degrees with the positive x-axis, or 5 pi over 4. So the first thing I'm going to do is kind of draw this thing so I can figure out where it is. So it's down here, and it has a length of 1. Well, if it has a length of 1, it's on the unit circle. Ha ha ha. And not only that, I know the reference angle is 45 degrees, or pi over 4, which means the lengths of the x and the y side are 1 over the square root of 2. Or if you prefer, you can do square root of 2 over 2. So the lengths are 1 over the square root of 2, or you can write it as square root of 2 over 2. But we're in quadrant 3, which would make them both negative. So whichever way you like to write these, those squared and added together, then taking the square root will give you a 1. So you know that it is the right vector there. And now we can go ahead and we've got this right here. So my angle 225 degrees actually comes around there. So B has to be, and I like -1 over the square root of 2. That's my preferred form. So I do -1 over the square root of 2, comma, -1 over the square root of 2. And then in terms of the standard unit vectors, I just multiply them by the standard unit vectors and write them. Oh, that was a weird one. Square root of 2, j hat. And that's pretty much it, right? Now, we do have adding and subtracting vectors using the standard vectors. So how do you add and subtract vectors? So we were adding and subtracting vectors before, and we were doing it on the graph. We were doing it geometrically. But you can also add and subtract vectors by just adding and subtracting their components. And you can do it either in angle bracket form or in the standard unit vector form. You can do it either way. So let me show you real quickly an example of this. Let's say that I have 9, 2, and I want to add that to -4, 3, all right? Well, in the past, what we did was we drew these on the graph, and then we used the triangle method or the parallelogram method. But we can also just combine the components in the most obvious way, which is add x to x, add y to y, and you're done. And that's the rule. So it turns out that this becomes 9 minus 4 is 5, 2 plus 3 is 5. That gives me 5, 5, right? You may go, no, that can't be right. Try it and see. The vector that terminates at 9, 2, and then the vector that terminates at -4, 3, if you translate this one to the terminal point of this one and connect the triangle, you'll get 5, 5, right? I know that sounds crazy, but that's what you're going to come up with. We have one last problem to do, which is an application problem. Now, this one is actually difficult. It's short, but it's difficult. And it's difficult because you have to think about what's happening and you have to figure out how to represent the different parts of the problem in terms of vectors. So let's read it once just to get a vague idea of what we're talking about, and we'll go back and pull it apart. An airplane flies due north with an airspeed of 550 miles per hour. The wind is blowing from the northwest at 50 miles per hour. What is the ground speed of the airplane? Oh, okay. Well, the plane's trying to go this way, but the wind is coming this way. And because the wind is coming from the northwest, that means it's going towards the southeast. And that south component is going to slow the plane down. That's what I'm expecting. All right, so we're going to go back and we're going to pull it apart. We're going to draw a picture. An airplane flies due north. Okay, so the first thing I'm going to do is I'm going to draw my all-purpose vehicle right here. Don't laugh, that's my best plane. And the plane is flying due north. And not only that, with an airspeed of 550 miles per hour. Now, the airspeed is the magnitude of the vector. So the magnitude of this vector, and we'll call this vector, well, I guess we should call it, we'll call it vector V. The magnitude of vector V is 550 miles per hour, right? That's the speed at which the plane is flying. Now, the wind is blowing from the northwest. So this is north up here, straight up. So we have due north. It's coming from the northwest, which means it's coming at a 45-degree angle from here, but it's actually headed towards the southeast. So if you want to draw it in standard position, then you would draw it from the origin down into quadrant 4, right? So you can do whichever way you want, but basically you have this one coming down here. It's blowing in that direction, right? So we're going to have this in standard position, my wind, and I'm going to superimpose a coordinate system like this. And then my wind is actually blowing from the northwest to the southeast. So in standard position, I'm going to have to draw it over here. Now the magnitude of the wind speed is 50 miles per hour. So I know it's a lot shorter. So, and it's coming like this. Now, how do I know it's at a 45-degree angle? I know it's at a 45-degree angle because it said northwest, which is 45 degrees off, which means it's blowing towards the southeast, which again is 45 degrees off. So I know the magnitude of this vector is 50, and we'll call this one W for wind. So this is W. And I know that the magnitude of W is 50 miles per hour. But I don't know the directions. Okay. Well, what can I do? Well, I could take a unit vector in the right directions and multiply by the magnitudes to get the vectors V and W, right? Let me say that again. I can take a unit vector in the direction the plane is traveling and multiply by 550 miles per hour, and that should give me the actual vector V. Okay, well, what would a unit vector going straight up be? Well, the unit vector is j hat. 0, 1, right? So this would give me basically vector V would be 550 miles per hour times 0, 1, which is going to give me 0, 550 miles per hour, right? Like that. Okay? So that is my vector representing the plane's motion. Now the wind is blowing towards the southeast from the northwest. So my wind is at a 45-degree angle here, but I just did one of those. And I said on a 45, 45, 90, the magnitude is 1, and it's 1 over the square root of 2, cosine and sine of 45 degrees. And because I'm in quadrant 4, the x component is positive and the y component is negative. So to find my wind vector, I take the magnitude, 50 miles per hour, and I multiply by the unit vector in that direction, which is 1 over the square root of 2, negative 1 over the square root of 2. And this is going to give me 50 over the square root of 2, comma, negative 50 over the square root of 2. And that's miles per hour. Right? Now, what do I do for the next thing? Well, the next thing is it wants me to know what is the ground speed of the airplane. So where is the plane actually flying? If the plane's trying to go due north and it doesn't correct for the wind, it won't actually be flying due north. It'll be flying a little bit this direction. So let's figure out what that vector is by adding V plus W together. So V plus W added together is going to give me 50 over the square root of 2, comma, 550 minus 50 over the square root of 2. That's the actual direction that the plane is going to be flying in, right? So it's going to be flying a little bit like this. Still mostly north, but a little bit to the east because it's being pushed both south and east. South is just slowing the plane down. Being pushed east changes the direction a little bit. Now it wants to know what the ground speed of the airplane is, and the word speed just tells you find the magnitude of the sum of those two vectors. So we need to find the magnitude of V plus W. So the ground speed is going to be that magnitude. So we're going to put this in magnitude, and then we'll take the square root, and we'll square both of these things. I recommend that you keep a scientific calculator handy so that you can use the calculator to do the more difficult arithmetic so you don't have to do it by hand. And when you work that out, you're going to come up with approximately 515.85 miles per hour. So the wind speed of 50 miles per hour slowed it down quite a bit. And the direction it actually ends up heading in is this direction right here, right? So if you're an airplane pilot and you need to go due north, you actually have to set your heading to the west. If you have a wind coming out of the northwest flowing southeast, you actually have to head that way to actually end up traveling that way. I hope this makes sense to you, and I hope you'll join me for the next video when we talk about vectors in 3 dimensions.